Infelizmente, yo no hablo suficiente español, así me tengo que hablar en inglés. I hope you can follow. Any questions are really welcome in case I'm not so very clear. However, thank you very much for inviting me to this webinar, to this presentation. Um, My name is Eric Ingelsberger. Maria already introduced myself, so I will skip this part and I will directly start with my presentation. Please let me share my screen. So Maria,
Perfect.
please let me know if we are online.
Yes.
Perfect. Yes. So my theme today is testing solution for composites. I will mainly concentrate on one of our testing instruments or better testing systems. But shortly or briefly, I will also introduce all our testing equipment and testing systems for the composites industry. Before starting with this topic,
I'm sorry, Eric. I don't hear you. I don't know if anyone else. Yeah, you're mute.
Yes, Eric, right now you have your microphone mute. Thank you, Paul.
so this was not by purpose. I'm very sorry. So,
Don't worry.
okay, then let me please start again. A moment. Yes, today I will speak about our testing solutions, testing instruments and testing solutions for the composite industry. I will mainly speak about one testing instrument or one testing system, but in the further presentation, I would also like to show all our other testing instruments, testing systems designed for the composites industry. Before going to details, please let me just very briefly, don't worry, introduce my company. You can see here an insight into our production hall. We are established since more than 75 or nearly 75 years. We are a private company, medium sized. We have about 60 employees in Mönchengladbach, which is in the heart of Germany, in the center. This also is a former textile center of Germany around Cologne, Düsseldorf, Aachen, Krefeld, some very well-known textile cities. We had the biggest spinning mill for cotton yarn in Europe a lot of years ago, but then a lot of production went out of Germany. What remained is machine production or engineering companies, and we are coming from this field of textile testing, but then entered into the composites industry several years ago. It's out here. We have a focus on composites industries since about 2010. We have one other daughter company in Austria, but they are really concentrated only on textile testing since then, or therefore I will just only introduce my company. We have, as you can see, a very deep production depth, starting from software design, mechanical production, electronic production. We have everything in our hands, 100% made in Germany. So we do not depend on any other sub-supplier. We produce all parts, electronics, software within our company in Mönchengladbach. And we are coming, as you can see here, from textile testing, which I mentioned already before. Well, now let me come to what I'm talking about today. I will talk about several parts. I have my presentation split it up in several parts with mechanical testing of single fibers, then go to single fiber pull-out testing. This is one of, you could say, the main theme of my presentation today. I will speak a little bit very briefly about matrix preparation, yarns roving testing, and finally also tape testing. Let me start with single fiber mechanical testing. Historically, or as it used to be, there was a roving tested here, which was impregnated, embedded in a kind of matrix, can be thermoplast, can be thermoset, and then there are two gripping fields here to grip, to clamp this impregnated roving. This testing method here is described in an ISO standard, ISO 10618. And as I said, we are testing the complete roving here, but we are concentrating on single fiber. Therefore, we do not take care of this roving testing, but instead going to one single fiber taken out, for example, out of a roving. So what are we doing? The classical test system is first you need to measure the fiber diameter, or better, the fiber cross section. In a first step, and then in a second step, you prepare such an individual or single fiber in, for example, such a paper frame. Both methods are standardized. The ISO 11567 describes the diameter measurement, and the ISO 11566 describes the tensile test of a single fiber. What you have to do? You first have to glue the fiber to this paper frame. Then you have two grips of the tensile tester, upper grip, lower grip. And the final step before being able to test is you cut this paper frame here with a scissor, and then you can start tensile testing. That means it will take a little bit of preparation time and a preparation energy to test such an individual fiber according to the ISO test method. We have found a solution to even not make this preparation of single fibers necessary. And this we can do with our Favimat tester. The Favimat is a tensile tester for single fibers. With this instrument, by the way, we have entered the market or the composite industry by only doing tensile tests of individual fibers. Here, we do not need such a paper frame to glue the fiber into, and we can measure the cross section and the tensile properties within one testing instrument. No need to use two different testing instruments. We are using a so-called vibroscopic test method, which I explain in 1 second, to measure the cross section. And we use direct clamping. We do not need this paper tabs. We directly clamp the fiber individually. Sorry. Some producers of carbon fibers which need to test a lot of fibers, they use an additional device which is called robot. Here, this is more or less a fiber handling system which can store up to 500 fibers and then test fiber automatically one by one. Let's have a look here to the testing zone of our Favimat. As I mentioned, you can see an upper clamp. You can see a lower clamp. This is necessary to do the tensile test, of course. And here we have a sensor head, measuring head, which is carrying out the so-called vibroscopic linear density testing. Let me show you how this works. This measuring head moves over the fiber to excite the fiber by a speaker to find the resonance frequency. And after finding the resonance frequency, then it will start a tensile test. So you can see the lower clamp here moves down to break the fiber. Sorry, of course, this is not a carbon fiber. You would not see a carbon fiber. Therefore, I show a picture of standard polyester fiber just to make it clear what the instrument is doing. But of course, it works with carbon also. So tensile test is now finished. Let me briefly explain what is the so-called vibroscopic linear density test. As you can see here, we have the upper clamps of the instrument. We have the lower clamps of the instrument. And we go to a certain pretension. And when measuring or when approaching this pretension, we know very precisely up to 0.1 micronewton precision the tension of the fiber. We know very precisely the so-called vibrating lengths of the fiber. And with the speaker system here, we apply a sound wave. You can see this here on the screen when I start the video. So this is the amplitude of the fiber vibration over frequency. And you can see here we measure the resonance frequency and finally find the resonance frequency as the maximum of fiber vibration. And from the resonance frequency, the length and the pretangent, we then can calculate the so-called linear density. Linear density is nothing else than weight per unit length. This is measured in PEX in the textile world, which is gram per 1000 meter fiber length. From this linear density, if we then include the density of the carbon, which is usually 1.8 gram per cubic centimeter, or the kilogram per cubic meter, we assuming a cylindrical fiber, we can then calculate the cross section. So this vibroscopic test method can be used to measure the cross section of the fiber, which is important. We do this on every individual fiber. So fiber by fiber, we first measure the diameter or the cross section and the tensile properties. This diagram here on the left-hand side would show the breaking force over elongation of individual fibers, and you have thin fibers, you have thick fibers, and this results in variation, a certain variation of the force. But if you then relate this to the diameter or the cross section we have measured, you will see the variation here nearly disappears because we do this for every individual fiber. Important is the operator time here for, I believe it was 25 fibers. No, 20 fibers, sorry. It is about 15 minutes. So after 15 minutes, you have your results for 20 carbon fibers. And now compare this to the necessity of measuring the diameter fiber by fiber and then glue this onto paper tabs and so on. So it's much faster. So far for mechanical testing of fiber. Now I would like to switch over to single fiber pull-out testing to measure the fiber to matrix adhesion. There are some macro mechanical investigations, macro mechanical test methods. There is even one standard, is an European standard to measure the unidirectional laminates determination of apparent interlaminar shear strength. The disadvantage of this macromechanical testing is there is a lot of influences to the test results. For example, the fiber orientation. Here you see all the fibers precisely in perfect alignment. All of them are parallel. But if you prepare the sample, which also takes some time, it takes some time to make the sample, to cure it, to harden it, and then to cut it, and then to test it. If the alignment of the fiber is not perfect, then this has some impact on the test results. Also the pore content, how many fibers, how many matrix in volume percent, the fiber distribution homogeneity. Of course, also the fiber properties, fiber diameter, this goes into the test results. Matrix properties certainly also, and fiber matrix adhesion, this is the property we like to measure. This also goes into the results, but a lot of risk of influence of uncontrollable or difficultly to control parameters. We instead choose to use a micromechanical testing, which is test of only one single fiber. And thereby we can exclude all this falsifying parameters, these falsifying effects, and only concentrate on fiber properties, fiber diameter. We already could measure the fiber properties and the fiber diameter with the Favimat. The Favimat also is part of this fiber to matrix adhesion test system. The matrix properties you can either get from the provider of the matrix or from literature, and what is left over is only the fiber to matrix adhesion. This is what we want to measure. I would like to introduce this system in detail. There are some test methods already very well known. One well-known test method here, this would be the microbond test. You take one fiber, you apply a drop of matrix, and then you simply pull the fiber through blades, and then you measure the force necessary to solve the fiber from this micro drop. Difficulty here is, of course, to measure the wetted length, the length where the matrix starts and where the matrix ends. It also has the disadvantage that during pulling on the fiber, the matrix will deform. You can distinguish those methods in methods where the force to pull out is, or here to push out, is applied to the fiber, or here applied to the matrix. We will only concentrate on pull-out test out of one single fiber out of a matrix drop. Here on the left-hand side, you see a test specimen which we produce using one single fiber here, which is embedded into a drop of matrix. In this case here, it is carbon fiber, and it is an epoxy matrix, thermoset. This crucible here is about 3 millimeters, very small. That means the drop of matrix which we need here is extremely small. It's about maybe 2 milliliters. And this means you can synthesize, for example, for producers of such matrix systems, you can synthesize only a very small amount of matrix to analyze. Well, the method of pulling out those fibers out of a spherical drop of matrix is developed at the Institute of Polymer Research in Dresden for the last 20 years. So the scientific work has not been done by Textechno, but we have developed this testing system with some industrial and research partners in Germany mainly. This pull-out test of the drop of fiber is most versatile. We can use, or we can do this test on any type of fiber. It can be glass fiber, it can be carbon fiber, it can be natural fibers or synthetical fibers, any kind of fiber. And we can also use any type of matrix. We could, for example, if we use a thermoplastic matrix, even go to higher temperatures than 400 degrees. That means we could also process PEEK as the matrix. We have, as I mentioned already, a cooperation with this Institute of Polymer Research in Dresden and the Fiber Institute in Bremen in north of Germany. And the scientific background is coming from them. Our part of this project was to produce a commercial testing system. And we used the Favimat, which I introduced before for mechanical fiber testing, as the pull-out testing instrument. So you already, when you are interested in this testing system, you already have a tensile tester for individual fibers, which measures the diameter or cross-section, tensile properties, and can be used for pull-out testing. This is the setup which we recommend. Favimat, I have already introduced briefly. It is a single fiber tensile tester. It measures the tensile properties, as I mentioned, fiber diameter, and it can do pull-out testing. Maybe here you can see a little difference. Before we only had two clamps, upper clamp, lower clamp, but here now we have an upper holder and a lower clamp to pull out the fiber. I will show you in detail. The Fimabond is the instrument used for sample preparation. So this sample or test specimen here is produced in the Fimabond and then transferred into the Favimat. But let me first concentrate on the Fimabond system for sample preparation. As I mentioned, any type of fiber, any type of matrix. This example here shows a thermoplastic. As you can see, we can go up to 400 degrees centigrade to process PEEK. In this example here, it is polypropylene droplet. You can see a small piece of polypropylene and then melted. Of course, the video you can see here is time lapse. This is not in real time. It takes some time to melt. This is the first step of preparation. And when the drop is melted, which of course also can happen under inert gas, for polypropylene not required, but to prevent oxidation of the matrix, we can use an inert gas flow inside the preparation zone. This is here. So this image is taken by a camera which is inside the FEMA bond, looking to the test specimen. I would like also to mention here on the top, I will stop this video in one moment. At the top, oh, sorry, you can see these elliptical light reflection. So this is coming from a lamp from the other side. And by clever placement of the illumination and the camera system, we then reach that the center of this elliptical light reflection is precisely top of the matrix drop of the sphere. So when, in this case of thermoplastic, the polypropylene is melted, the next step will come here, and you see the fiber here. And the fiber then, as you see here, touches exactly the center of this light reflection to be sure that the fiber is exactly on the top of your matrix drop. So this is the embedding. When I say that the FEMA bond only prepares the specimen, this is not completely correct, because it can also do some measurement, which I would like to show you right now. There is a second camera looking exactly from the side, perpendicular to the fiber, and it can here measure the fiber diameter. So we have a second option to measure the fiber diameter. And let me start the video. While inserting into the matrix, this is a matrix surface here, we can measure the wetting angle. This is used by or done by picture processing on the picture taken by camera 2. And this here we measure the angle of wetting. There are some methods to measure this angle of wetting, which, for example, is important for a rapid transfer molding, where you insert the matrix into a woven fabric or multi-layer fabric. This could or can be measured actually currently only with a simulation, for example, with water. But here we can do this in situ. That means we can do it even at 400 degrees of centigrade with a real matrix. We do not need any, or we do not use any simulation by water, for example. Here the image analysis is focusing on exactly this point where the fiber touches the matrix drop. Last step is, in this case of polypropylene, of course, the hardening or cooling down. You can see by the surface that now the droplet cools down. And then the specimen is ready for testing. Here we, for example, show a glass fiber insertion into epoxy. So this is thermoset, no more thermoplastics. You can see here the temperature profile of the heating system inside the FEMA bond, which is here first preparing the matrix for embedding. So in this period here, we embedded the fiber. Then we bring this to curing temperature to a higher level. And then this is cooling down. There are several ways of cooling down. We can passively cool it. We can actively cool it very fast. And this temperature profile here, you define before starting to embed the individual fibers. As I said, we can measure the wetting angle with the second camera, and we can now see both curves in one. You see here, this is the moment where the fiber is embedded. And you see the contact angle or embedding angle here. And during cooling down, the angle moves or returns, or reduces. This means there is a certain shrinkage of the epoxy while cooling down. This is report which you will get from the FEMA bond. So FEMA bond also can measure some properties. However, after preparing this test specimen with the FEMA bond, we then transfer it into our Favimat. And as I said, we have some different clamping system here. Now, this specimen is turned upside down, so the fiber is then hanging down, gripped by a clamp, and taken out of a specimen holder, which you will see in detail right now. Here you see the droplet, the matrix coming from the bottom, from the top side, moving down, and by mechanical adjustment and looking with a camera, microscopic camera, adjust the system that way that first the fiber here touches the clamping area. Here, for example, it moves too much to the right, so it now is not touching. Now it is touching with the perfect alignment. We, in the last step here, reduce the free length of the fiber to reduce or eliminate as much as possible the elongation of the fiber, elongation properties of the fiber. Then we close the clamp and we start pulling the fiber out of the matrix. The next video shows impressively what happens during this pull out process. Here you can see the matrix drop. It is a transparent polypropylene. And here you see the fiber which is embedded into the matrix. Certainly during preparation of the test specimen, you define the embedding speed, how fast this is embedded into the matrix, and you define the embedding length. This is the length here. When you start pulling out, you can then see that the fiber first will create a crack. You will see this in one moment. Now the crack here moves up until it is completely debonded, and then the pull out will continue, but only against the slippage of the fiber inside the matrix. So there are two important points, or three important points. The first is the point where the crack initiates. This is the force or the stress where your composite starts to fail. Then we measure the maximum force, and this will drop. The force will drop at that moment where the fiber is completely dissolved. So not only after the first crack. I will repeat the video. The first crack is created. The crack penetrates into the matrix and then is completely dissolved. While doing this pull-out test, we measure the displacement, that means the movement of the lower clamp, and we measure the force. What is resulting is a force over displacement curve. And if you watch the curve format here, you can see there is a little kink in the force displacement curve, and this is where the crack is initiated. This is where the crack happens. Here we see the maximum force. That is the moment where the fiber will completely dissolve, from the matrix. And then the force will drop down, resulting in, if you continue the tensile test, in only friction. And because the fiber is slipping out more and more out of the matrix, the force will drop down. Well, if you look to this specimen here, you can see this meniscus. We only have embedded this depth, and this meniscus will be created either by increasing contact angle or by cooling down. This is unpredictable. You do not know. Therefore, to know the embedded length, you cannot rely on the depth which you have defined while creating the test specimen. And because of this meniscus, usually there is some additional length. And this complete wetting length or embedding length here is measured when the force drops down to 0. Here, the fiber is completely pulled out of the matrix. So then you know the length which is embedded into the matrix. These are the forces which do not help you very much because you do not know was it a thick fiber, was it a thin fiber. Therefore, you need some more parameters. And please do not be shocked from the formula which will run now through the image. This scientific work has not been done by TexTechno. This is the part which was done at the Institute of Polymer Research. With this formula, we then can find the interfacial shear strength, the apparent, this is the maximum force, which you get by testing with macroscopic measurements, and by analyzing the form of force elongation or force displacement curve here, we can find the so-called local interfacial shear strength, which is where the crack is initiated. Just to make it simple, the formula for the apparent interfacial shear strength is simply the maximum force divided by the wetting area. This is the embedding and the embedding length, which we measure here, and the circumference of the fiber. I will not go into this formula in more in detail. I just have to accept it. Let me now show you some examples from real life. This here, for example, is a comparison between a standard and a surface treated carbon fiber embedded in PEEK. So this is the standard fiber, and this is the surface treated fiber. And as you can see here, this is the apparent interfacial shear strength, only measured by the maximum force. This is the standard fiber, and this is the treated fiber. This is where the crack is initiated, the local interfacial shear strength. And this finally is the energy release rate. And you can see very clear differences between a standard and a treated, surface treated carbon fiber. The next example is a carbon fiber embedded in polyamide. The fiber here is unsized. There is no sizing on the surface of the fiber. And here these are some special contact improving sizings or contact improving sizing on the fiber. And here you can see the standard and the sized fiber. That's the apparent interfacial shear strength only by force. You can already see this by looking to this force displacement curves. This is the local interfacial shear strength, where the crack is initiated, and the energy release rate. Next, I would like to show some different combinations of fiber and matrices. This here is a carbon fiber embedded in PEEK. This here is a glass fiber embedded in a polyamide fiber, a polyamide matrix, sorry. A glass fiber embedded in a thermoset epoxy matrix. And this is, oh, sorry. Here you can see modifications of the fiber, and here you can see modification of the matrix. This is a polypropylene modified and a standard polypropylene with identical glass fibers. Here, because we are using the same scale, the difference looks smaller, but if you would magnify this, it would show you a very clear difference. This example here shows the optimization of a matrix. So what we have here are glass fibers, tape of glass fibers, embedded in polypropylene fiber. So this is the matrix here, and this is the reinforcement fibers. And then this will be pressed and melted. And this study was made together with a German company of PHP fibers. They wanted to know at which weight amount of maleic anhydride added to the polypropylene fibers, you would have the best fiber to matrix adhesion. Well, this has been found at 6 weight% of maleic anhydride. This example is also quite interesting. This was made with a company Ahlström Mundsrö. They produce blades of wind generators, electric wind generators, and they had a very big complaint about delamination. So when they produced their glass, I think it was glass too, let me see, not sure what it is. However, they produce this composite, and they had the problem that the composite delaminated, and they wanted to know what was the reason therefore. So they had a very big complaint about the quality. There was some quality complaints from the final producer of this blades, of this composites. And we could prove by our FEMA test system that there is an effect of aging of the sizing. And even they have received a wrongly labeled sizing. So they put a wrong sizing on their fibers. Therefore, it would be a good idea to use our FEMA test system as an incoming quality control measure to see if the sizing is as expected. There is an effect on the sizing on the apparent on the apparent interfacial shear strengths based on the maximum force, on the local interfacial shear strengths, and on critical energy release rate. Interestingly is the company of Ahlström, they already do some macromechanical testing. This is a so-called transversal tensile strength test. Here you can see a model of the test specimen to check if the quality of the final composite is good. The disadvantage of this test is it will take about 2 weeks before you get results. With our system, you get results in two days already. There is some time required, of course, to cure or to harden the matrix precisely according to the producer's parameters, producer's regulations. Here you can see between sample 1 and sample 2. Sample 1 is the fresh right sizing, and this is wrong sizing. You can see big differences in the apparent interfacial shear strengths, the local interfacial shear strengths, and the energy release rate. This is measured by Ahlström, so they could also get the results, but as I said, with a delay of 2 weeks. Speaking about comparison of micromechanical testing with single fiber pull out and macromechanical testing of a complete composite, the correlation is okay, is good. Well, this figure is taken out of the habilitation of Dr. Mäder, which was one of the professors, a lady, which was involved in the scientific work, which is the background of our FEMA test system. We have already created a so-called DIN spec, which describes our testing method. A DIN spec you can think of like a pre-standard. If you are familiar with the ISO world, then this would be a technical specification. So this DIN spec you can download for free. I can, of course, publish the link. It precisely explains and shows how the test is carried out, which influences are coming from which parameters. It precisely describes how to do the test. As I said, download is free of charge. It was publicly available. And there will be an ISO standard in the future. As Maria already explained, my job is part of my job is doing standardization work. So I'm a member of the DIN. I was the project leader of the production or the publication of this DIN spec. And now I'm also the project leader of the ISO creation. I have last week participated in an ISO meeting in Stockholm in Sweden, where it was concluded that this standard ISO standard in progress will be published. It now is in committee draft stage. It will then be published probably latest 2026, but it is in progress. So there will be an ISO standard describing exactly the method which I introduced with our FEMA test. That's it for single fiber pullout testing, interfacial shear strength. Just very briefly, matrix preparation. What could happen if you prepare the matrix, especially polyurethane matrices, manually, is that you will have a certain bubble effect. So there's a bubble creation because the matrix does still contain some humidity. So manual mixing would or can result in bubbles, which of course then will falsify the pull-out testing results. Here we have been looking for a small vacuum mixer, but there was no mixer available on the market for a reasonable price, reasonable size. So finally, we decided to make this small mixer ourselves. This is again a commercial available testing instrument or preparation instrument, small vacuum mixer. This double action. They have 2 containers inside. You will see a video running in 1 second. And by using the evacuation of the air vacuum mixer, it will take out the humidity of the matrix and then thereby prevent bubble creation. As you can see here, this is the same matrix with bubbles, manually mixed and mixed with our FEMA mix system. We can here close the lid. We have, as I mentioned, 2 containers. We can mix very small amounts of matrices. It's not a big instrument, it's a very small instrument, good for laboratory applications. I will see this, you can see this in operation right now. There are 2 containers, and then by centrifugal asymmetric mixing, you will then evacuate this or remove the humidity by vacuum creation. And then you have matrix prepared, which prevents the creation of bubbles. You, of course, can adjust the mixing time. You can adjust the mixing speed. You can also define the under pressure. Of course, you try to do this as in a good as possible vacuum. Is a table instrument, very small one. And this is a small instrument which we, to complete the line, also offer. Now I would like to move away from single fiber testing. I will then go to yarn and roving testing. First, this is our Statimat 4U. There's a quite big tensile tester for high tenacity yarns. This can test up to 5,000 Newton breaking force. In addition to the tensile testing zone, which you can see here, we also can, by using the so-called auto count module, measure linear density. This is weight of a certain length of yarn. Well, why do I show you this instrument? Because we have found a very interesting effect, which we did not expect. Here we have tested through a glass roving, and this shows the weight in gram per 1 kilometer length, which at the start had a certain value, and then going deeper into the package, the linear density means the weight or even the diameter of the fibers increased, something which we did not expect. So we used this instrument, we started to use this instrument only to test tensile properties, but then found this interesting effect. Just only very briefly about the tensile tester. One more small instrument which we recently have produced and put on the market. This is a reel. In the first moment, this looks like a standard reel, which you could, for example, use or which is usually used to measure the weight per length. That means you will create a hank of roving and then put this onto a balance. But if you look to the details of this roving, of this reel, it has some nice features which have not been available with any other reels worldwide. The first is here we have a protective housing. We move this housing completely about the haspel here. That means there is no risk of any injury. Now, it is completely encapsulated, which makes it interesting for universities, for research laboratories, where you find students working with this instrument. So there is no risk of uh, hurting yourself. Of course, not only students. This is a common effect, a common thing that maybe you know this from operating a reel yourself. Maybe you have been already hit by the reel, and then you will remember, or you can understand that this is a nice feature that is completely encapsulated. It is now following the machine regulations for work safety, no possibility to hurt yourself. And another very nice effect is it is very powerful. The torque is very high, so that means we can then strip off the yarn tangentially, which is shown in the next video. This here shows the text reel in operation, and as you can see here, it is stripping off tangentially. This is a carbon roving, this is a glass roving, and the torque here is good enough or high enough to overcome the braking effect or the brakes here of the rovings, because you must mechanically brake these rovings. Otherwise, if you stop, they would continue rotating because of their mass. So it's even looking in the first look, the first view, simple instrument, it has some really nice features. Now I would like to come to a testing instrument, which we again have created with some industrial partners. The background here is what happens during the processing of a roving. There can be some negative effects during processing. For example, if you use such a creel here, where you apply a lot of rovings and then you pull off or strip off the yarn from this roving, you may have some friction along guiding elements, which can here, as you can see here, create breaks of the individual fibers or filaments. So that means everywhere where you have some surface, you can get some fiber breakage, for example, or some effects which might disturb during a production. And we have then created a testing system which is of modular design. You can see we have different modules for different applications. And these modules you can freely combine to whatever you would like to measure on the roving during processing. I will then step by step go through all these modules and show you the function. Here in the first, this is a module which you always need, of course. This is a wind up module. It can also measure broken filaments. I will show you in a while. Eddy current, this is used only on conductive rovings like carbon rovings. The parallelism, the alignment of the fibers or filaments, if they are all in same alignment, all in the same direction, or if there is some error in fiber orientation, we can measure the friction and fuzz creation. I also will show you a video explaining this in detail. We have camera systems here before and after a spreading unit. This is to make a tape out of roving. So you make this roving and bring it to a tape. This is quite important and a common production step. So we measure the width before and after the spreading. And finally, of course, we have a wind up unit, which again measures broken filaments created during running of the yarn through this testing instrument. So it's a dynamic testing instrument measuring properties on running thread, on the running roving. Let me show you in detail. This is the wind up, the wind off module. Here you have two things. First, this is the measurement of broken filaments and also measurement of force. I will show you here in detail. Here, the roving runs over the force sensor. And in parallel, here you can see this little red light measuring the number of broken filaments which come from the package or come from the roving, the spool. So thereby you can already check if there are some broken filaments coming from your package already. Here you can, for example, see the number of broken filaments. We have here defined a length of 100 meter, and after 95 meters approximately, we have found 17 broken filaments at the entrance and 54 broken filaments on the exit. That means during the movement of the roving through the testing instrument, some fiber breakage has been created. And we measure the in-running and out-running force. That means we can then also measure the coefficient of friction. For example, if we would have a friction module. The sample width here, these are the two camera system. Let me go back. First camera system, second camera system. So now you can see the width of the roving before and after spreading. I will show you some more details on that. This here shows the friction unit. So here the roving enters onto these two rollers here, move over the friction body. In this case, it is a ceramic guide, but it can be also glass or metal. We can even here include some elements of your production machines. As I mentioned in the beginning, we have a very deep production depth. That means we can then easily include your components, if you like. You can see here there are some fiber breakage created by the friction. And here you also can see some fiber waste falling down. Here there is a air suction through a filter tissue. So after the measurement, we can measure the weight of the fluff, fibers broken during the friction here. And if we know the incoming force, I mentioned we have a force sensor here at the entrance and at the exit, we can then measure the coefficient of friction. For example, as I mentioned, your elements of your creel we can include here. This is the in-running force here, the outrunning force, and thereby we can measure the coefficient of friction along the yarn, the length. Now let's go to spreading. What we see here, this is a heated bar spreader consisting of 5 different bars, which are heated. We can go here up to 300 degrees centigrade, and the wrap angle we can adjust up to 600 degrees. This is a spreader which of course was not produced by Textechno. Here we have taken a commercially available spreading device. This can be also your spreading device. We have some alternatives already with this, which is a simple bar spreader without heating, or ultrasonic spreaders, any type of spreader we can use here. This gives you a better image. Here you can see the width of the in-running and the width of the outrunning roving. You see it is now nearly in the form of a tape spreaded. This is the camera system. It is a line camera system. You can see the red illumination here. And here these are some images of the in-running and the outrunning sample. You can see that the width of the sample, width of the roving is of course spread. This is what basically is the target of a spreading device. Some examples of measurements. This is quite a good roving. This roving here is very uneven. That means the spreading is not as perfect. This can have several reasons. This can be, for example, a sizing effect, or what you can see here. This is a twist inside the roving, which then of course prevents that the fiber band, the roving is completely spread. And you can see some gaps in between. Means if the fibers separate, if they are not evenly distributed during the spreading. And then, of course, as a last device here, this is a wind up. Sorry, let me go back. Wind up again with a broken filament sensor and a force sensor, and then the roving is wound up again with a traversing. The idea of roving testing we have taken into tape testing. The tape testing device is only very briefly one slide. This is one of the latest developments which we have shown this year at the GAC World exhibition in Paris. The principle is nearly the same as roving test, and we have some new ideas included into this tape testing. This again was designed with some partners, some industrial partners, which is, for example, the Fraunhofer Institute. This is V-Carbon. Altex is involved. Sodagus, they are producers of this eddy current testing system. Here we have a wind-off device, same as with the rovings. We measure broken filaments and tension on the in-running and the outrunning. This here is the drive, which is driving or moving the tape forward, and it's wound up again. Here we can measure the friction, as I already explained with the roving tester. Of course, with tape, you cannot expect that you have some fluff generation, but you first can measure the coefficient of friction and the creation of broken filaments, of course. We measure with a triangulation system here the width and the thickness of the tape. We measure the fiber orientation. This is by eddy current, and this is by polarized light. And we can then finally also measure thermographic effects, where we heat up the tape and we watch the tape moving along a sensor to see how homogeneous the temperature will move down. And this gives you some indicator of the fiber content or the matrix content. So with this description of our testing instruments, I already come to the end, and I would like to give a short summary. We can do tests on individual fiber, mechanical testing here with our Favimat, maybe in combination with the robot, or breaking tenacity, modulus measurement, diameter, cross-section measurement. We can also measure fiber to metal friction if desired, or bending stiffness in combination with the FEMA bond. This creates the FEMA test system, and the FEMA test system, for example, also has been Innovation Award winner of the GAC in 2016. We have a tensile tester for reinforcement yarns and rovings. I showed you the effect of weight per unit length distribution along a glass roving. We have our roving test for roving measurements, process properties of rovings, and finally out of tapes. And final remark, we do not only produce these testing instruments, we also offer you a commercial in-house testing service. That means if you have some samples and you have some doubts, we could also offer testing those materials, which is mainly fibers and matrices for fiber and matrix adhesion, which, by the way, also is not only interesting for fiber producers. As I also mentioned, it is interesting for sizing producers, for matrix producers, universities, research institutes. All the other instruments also are very flexible in the application, and we can offer commercial testing service on all our testing instruments. And having said this, I will come to an end, and I would like to thank you very much for your attention. Thank you very much.
Eric, thank you so much for your presentation, a very complete presentation. I don't know if we have any questions from the people joining us, but if we don't have any question, I would like to ask you something. You talked to us about the ISO, and all this that's happening in Europe will sooner or later come to Latin America. So I would like to ask you a little more about what's happening or what will happen with this ISO that you told us about, the 1937 about fiber reinforced composites measurement of interfacial shear strength by means of micromechanical single fiber pull out test? Like maybe you can give us some insights or some information that we should have like in mind of what will happen and what will come with this ISO in the future.
Yes. As I mentioned, there is a free of charge download possibility of the DIN spec, and the ISO basically is the DIN spec with some modifications. There are some some ISO regulation, some ISO rules of how to write a standard. For example, you cannot include any person or any company into an ISO standard, but you can do with the DIN spec. That means if you download this DIN spec, you will find all people involved in writing this DIN spec standard. And in the ISO, you will not find this. But the ISO will look very similar to what the DIN spec is looking like. As I mentioned, I had the honor to be the project leader of the DIN spec, and thereby I now am project leader of the ISO. The ISO has been published as a working draft. Working draft means this is the group which is doing the technical work to develop a standard. It's not a political, it is a technical committee. And they give some comments of maybe we should include some more information, or they need some explanation about the process. And my job is then to answer the comments, which is given by the working group members during the creation of the ISO standard. So that means finally, if you download this DIN spec free of charge, you are already more or less on the same track as the ISO will be. It is only on individual fiber pull-out testing, which I have explained with our FEMA test system. There is no other commercial testing instrument available. Well, during the meeting last week in Stockholm, I heard that there is one instrument from Japan, but it has some disadvantages. For example, they do not use a spherical matrix. They use matrix which is filled into a hole drilled into a metal plate. And this means during pull out, the matrix will deform because of some elasticity in the matrix and some poison parameters. This will falsify the testing results. So we believe that our testing instrument is the better solution because we are using a spherical matrix, and this is one commercial instrument which is based on industrial, universital research results, research studies. So it will be the only standard based on the only available commercial instrument. Does this answer your question?
Yes, yes,
Good.
thank you very much. We have a question from the attendees. Gustavo Barreras, if you want, you can open your microphone.
Hi, good morning, everybody. Eric, thank you so much for sharing this important information. Currently, I work in a company that produces unsaturated polyester resin, and one of the issues that we have currently is trying to test the wearing capability of the resin compared with another kind of resin, of course. Which mechanical property do you recommend to test wearing capability of resins?
Most probably, sorry, this will be the most interesting, or one of the most interesting measurements, which is done in the FEMA bond. Here we measure the wetting angle. So matrices with different wetting properties certainly will have different wetting angles here. So the wetting angle, as I showed in this graphic here, is shown during embedding and curing of resin, of epoxy resin here. And you will see different angles here with different wettability properties of your fibers or of your matrix.
Okay, thank you. Very, you have to get this kind of equipment. Well, we have one equipment to test weighting angle of fillers. Of course, we cannot do an adaptation of this equipment for fiber, right? Or do you know some adaptation of this kind of equipment to test weighting angle of fiber?
Yes, you can measure the wetting angle of fibers. There are some equipment. Unfortunately, right now, I do not know by mind, by my head, by my memory, which producer will offer such instruments. It is usually you insert a fiber into a liquid and measure the force which is created by uh, moving the fiber into the liquid or pulling the fiber out of the liquid. But this is usually a simulation of using water as a liquid and ambient temperature. You cannot do this under temperature. Here we can do this under temperature. And we can do this on the real matrix, which gives some more advantages. Then you can see what really happens to your matrix and your fiber instead of only doing a simulation. If you like, I can find out some distributors or some producers of such wetting angle equipment for individual fibers. But right from my memory, I don't know.
Thank you, Eric. Thank you, Eric, for this information. Thank you so much.
One final remark, if you have some doubts if this is working or not for your fiber and matrix combination, we could do some tests and send you a test report.
Oh, thank you. I'll appreciate it.
Okay, thank you, Eric. I don't know if we have any other question. I don't see any more questions here. Anyways, Eric, thank you so much for all this information. I think knowing about these new technologies and all the things that you are doing around testing solutions is very important for us here in Colombia and for the sector, of course. I will share this information with the attendees. I will share the memories. I will share a glossary as well, and some articles that have been out regarding this topic. And I will also like to share with you that we opened our Almaco's YouTube channel. So we're going to upload this video there too for you to follow us. You can find us as Almaco Colombia. I think that would be all if we don't have any more questions. Eric, Carlos, thank you so much for preparing this presentation for us. And you are going to leave us your information, right? Your email one.
Certainly. I hope it was not too long, the presentation, and I know that there are a lot of information in the presentation. Therefore, please, you are heartily invited. If you have some questions, some doubts in the future, please contact Carlos Franco or contact me directly at TextTechno. I will publish my email contact data.
Perfect. Perfect, Eric. I think it was a very complete presentation. So we're gonna share this information. We're gonna share your personal information for any person who wants to contact you. And that would be all for today.
Thank you very much for giving me the opportunity and for your time and attention. Thank you from my side.
Thank you. Okay, thanks everybody. Have a good day.